At the moment, we have a model that's going to draw a hyperplane to best separate our two classes. And since most of the time it's impossible to completely separate our two classes, the model has some built-in slack, has a whole idea of margin violation. So we have a hyperparameter that's going to tune, and we can play around with and tune to see how much importance should we add to margin violations as opposed to minimizing the margin violations. So it's going to try to best configure that hyperplane going through the points to separate them given the chosen value of C. But ultimately what we have here is a linear classifier. It's still drawing a line in 2D space. In higher dimensions is drawing a hyperplane in our p-dimensional space. And using a line or a hyperplane is not very flexible. We want some additional power to draw non-linear decision boundaries. So we can make some modifications to our model. So let's have this example here. So notice we have blue points surrounded by, we have these blue points that are surrounding these red points. And we can try to go ahead and apply our current model, try to figure out where should it draw the hyperplane to best separate our two classes. And you can visualize that it's going to do a poor job. Using a linear decision boundary is going to do a poor job to separate my two classes. I need something to draw something that's non-linear. So let's see what we can do to remedy this issue. So one thing we can do is we can go ahead and create a new feature. In this case, we're going to call a feature x of 3, which is going to be the distance from the origin of our original feature space. So the square root of x1 squared plus x2 squared. That's our new feature. Since we have 2 dimensions, now we're going to project, essentially what we're doing now is we're projecting our original features, our original data points in these 2 dimensions. We're going to project it to a higher dimensional space. In this case, 3 dimensions. So let's visualize what happens if we were to project our data to that new dimension that we defined. So that's what this block of code is going to do. So now notice we have that x of 3 dimension. Now the question is, in this new dimensional space, this higher dimensional space, can we draw a hyperplane to separate our two classes? You can fool around with the view, but notice what I want to show you is that yes, by including this new feature x of 3, we're projecting our data to a higher dimensional space, it becomes possible, or we're going to have a better model to separate our two classes. Let's see if I can get a nice view of what's going on, a better view. Maybe if I flip it this way. What I'm trying to show you is the plane that's dividing our two classes. So I'm flipping it and you can see the plane that is doing a pretty good job of separating the two classes. Not perfectly, but definitely better than we had before. We have here is a link of a very similar visualization. I'll go ahead and play it for you. So in this situation, we cannot draw a line, or we could draw a line, but it's going to do poorly. We want to go ahead and have a circle as our decision boundary. So we project to a higher dimensional space. That's what's happening there. And then in this new space, we can draw a plane. So we have a plane that's going to cut through that shape. And we can also visualize what is the resulting decision boundary as a result of projecting our points to a higher dimensional space. And that decision boundary is no longer going to be linear, it's going to be non-linear, in this case a circle. So in the example we did before, we directly included this non-linear term into our data set. So we went from 2 features and created that new feature. However, the way we traditionally solve the objective function we define up above is going to allow us to indirectly apply the projection using something called the kernel trick. The kernel trick is going to use a kernel, which is a function that creates the implicit mapping projection to the higher dimensional space. So in other words, by using the kernel trick in the governing equations, we don't have to directly apply the feature generation. And that's nice because we don't have to increase the size of our data set, increase the number of columns. Additionally, since we can apply this kernel, since we're using this kernel, we can easily swap out one kernel over the other. Remember, what this kernel is doing is it's applying the projection to a higher dimensional space. It's doing so implicitly. There's no need to manually create the features and expand my original data set. This is all possible given in modifications of our governing equations, which we'll look at the very end of the notebook. We'll look a deeper dive behind this kernel trick. Okay, so let's talk about our choice of kernels. So these kernels are going to do the mapping to a higher dimensional space. So there's several kernels we have available for us in scikit-learn. So at this point is when most people call what we have here our support vector machine model. A model that's going to be capable to handle these kernels to allow you more power in your predictive ability. Since we're no longer restricted to using just a hyperplane, or essentially what we're happening here is we're able to project our points into a high dimensional space and to do the separation there. So common kernels we have in scikit-learn are things like the linear kernel, which is sort of the standard one, the soft margin classifier as we saw above, so basically no transformation. We have the polynomial kernel, so we're going to apply those polynomial terms to our features. There's also the Gaussian radial basis function kernel. This is the most popular one and the most powerful one. So that's the one you should always try initially. If you try that one initially, if it doesn't work out, you can go try the other ones. You also have the sigmoid kernel. A nice thing about the radial basis function kernel is that there's only one additional hyperparameter the model is going to introduce. If you look at the other kernels, look at the degree one, there's R and gamma. So we have to choose what is the value of R, what's the value of gamma. Same thing with the sigmoid. We have to choose the value of gamma we're going to use and the value of R. But for the radial basis kernel function, there's only one additional hyperparameter. It's going to be a lot easier to tune that model. And in fact, an interesting note about using the radial basis function kernel is that it's equivalent to projecting our vectors into an infinite dimensional space. And this would not be possible to use the radial basis function kernel without the kernel trick. In this block of code here, we're going to allow you to play around with different kernels. So we have our points here. Notice we cannot, we can use a line, but it's not going to do so well given this curvature. So we have to have a model. We have to use a kernel that can model this curvature that's required to best separate our two classes. So I can go here and choose something like the RBF. And there you go. Notice using the RBF, and I didn't even fool around with any of the hyperparameters right now, I was able to create these two zones, this nonlinear decision boundary. You can play around with things like C and things like gamma.